This video covers the standard operating procedure for our Hewlett-Packard 5890-5971 gas chromatograph mass spectrometer. The large box in the center is an oven and contains the capillary column for our separation. The detector is the small unit at the far left and contains a quadrupole mass spectrometer capable of scanning up to 600 atomic mass units. The helium carrier gas is supplied from a tank behind the instrument. Please note the pressure on the tank as indicated at the gauge on the right. The helium should be left on at all times. If this drops below 200 pounds per square inch, please notify your instructor. The heart of the gas chromatograph is the separation column. Modern analytical columns are made from fused silica capillaries. Typically, these columns are from 25 to 50 meters long. It may seem surprising that glass can be coiled like a wire. Glass is actually quite tough and flexible if one can prevent scratches on the surface. This capillary appears brown because it has a tough polyimide coating on the outside to protect from scratches. Capillary is an open tube through which helium gas carrying our sample will flow. The outside diameter is typically 250 to 300 microns. The inside diameter is usually around 200 microns. The inside wall of the capillary is coated with a very thin polymer film. This thin film acts as a solvent or an adsorbent for our sample molecules. The sample components separate based on their differences in speed moving down the column. The differences in speed among the sample components depends upon their vapor pressures at the column temperature, as well as the intermolecular forces between the sample molecules and the stationary coating. You can check out the GC column by opening the door to the oven. The latch for the door is in the lower right-hand side of the oven. The column is supported on a wire frame. It is connected by means of special fittings to the injection port at the top of the oven. Samples injected here quickly vaporize and are pushed onto the GC column using helium carrier gas. The other end of the column exits through the oven wall to the left and goes on to the mass spectrometer. Let's take a closer look at the injector. It can be heated separately from the oven to a high temperature that ensures that the samples vaporize quickly upon injection. Sample is introduced from the top through a rubber septum. Helium comes in from the right, pushing the sample toward the capillary at the bottom. If we let the sample gas fill the entire injector, it will take a long time and a large volume of helium to push it all onto the column. Furthermore, even microliter amounts of sample will overload the stationary phase on the capillary. The most common remedy is known as a split injection. We introduce another opening at the bottom to allow gas to escape. This is known as the split vent. We also confine the sample to a smaller volume by inserting a glass liner. Often the liner contains a small bed of silica particles coated with stationary phase at the bottom. The particles enhance the vaporization and help focus the gases. As sample vaporizes inside the glass liner, it has two ways to escape. A very small portion goes down the capillary, while a much larger portion goes out the vent. The oven temperature can be set manually from the controls on the front of the panel. Type in the new value and press the Enter key. You can also set the temperature of the injection port, which is in position B on this instrument. The upper limit is 280 degrees centigrade on this instrument. The separation column passes through a short transfer line between the oven and the mass spectrometer. This zone should also be heated to 280 degrees. The computer controlling the instrument is normally left on. To launch the software for the instrument, click on the icon labeled MS Top. Begin your work for the day by tuning the mass spectrometer. From the Tune menu on the far left, choose Standard Spectra Auto Tune. This procedure takes a few minutes, and you may want to see what is going on during the tuning process. If so, click the menu bar on the bottom right-hand side of the screen that says Instrument Auto Tune. Inside the mass spectrometer, a valve opens, leaking in vapor from a fluorinated compound to the detector. The instrument uses the signal from 3 different fragment ions in order to optimize the response of the detector. Once the instrument has satisfactorily tuned the detector, It very briefly displays the full spectrum of the standard and then automatically prints out a report. Notice on the top of the report that the heavy isotope peak at 503 is clearly distinct from the peak at 502. On the bottom half of the report, check for leaks from the atmosphere by looking for peaks for molecular oxygen at 32 atomic mass units and molecular nitrogen at 28 atomic mass units. These should be less than 10% of the base peak height. If they appear larger than that, then the septum in the injection port needs to be changed. Please notify your instructor. Save the report by placing it in the drawer below the computer for future reference. Exit from the screen to return to the main menu. To create an experimental method, select Edit Entire Method from the pull-down menu item entitled Method. For most sections, we will leave the default items in place. For example, we have the HP 5890 gas chromatograph. Click OK to acknowledge that the parameters for the mass spectrometer that have been saved in the tuning process are in a file called atune. Most of the time, we will want the instrument to record a full mass spectrum virtually as fast as it can. This gives us the maximum amount of qualitative information. However, some situations our sample will be very dilute and signals will be very weak. We can enhance the signal by spending more time monitoring only certain selected ions. This can yield as much as a factor of 10 improvement in the signal. We will choose the scan mode for this demonstration. In the next window, we will set the time at which the mass spectrometer turns on. This is called the solvent delay. Usually, our samples are injected as a solution. Even a microliter of solvent is an overwhelming amount that can damage the detector. To avoid damage, we wait to turn the detector on until we're sure that the solvent has had time to move through the column and exit the detector. If you don't know how long your solvent takes to move through the column, then set up an experiment with no solvent delay and inject only vapors from the solvent you wish to use. Ask your instructor for help if you want to do that experiment. On the same screen, you can also set the mass range for the detector to scan. If you're not interested in very small molecules, you can start the scan at 35 atomic mass units. This avoids traces of air and water that may have leaked in through the septum. Set the high end of the scan to be slightly above the mass of the largest molecule that you expect. Note that the wider the mass range that you scan, the longer it takes per scan. That will yield fewer data points to define a given chromatographic peak shape. You also have the option of defining the mass range for 3 different windows. If you wish to implement this option, set the start time for the second and third windows on the left-hand column. Click OK to move on. On the next screen, we set the various temperatures for different zones in the instrument. Note that a compound will move at a significant rate, even 100 degrees below its boiling point. Near the boiling point, there will be no retention for that compound at all. The set point at the top of this screen indicates that this experiment will begin at 40 degrees centigrade. The box marked Initial Time indicates how long the oven will spend at 40 degrees before changing the temperature. Below in the table, we have the opportunity to raise the temperature at a specified rate. We have chosen 15 degrees per minute, up to a final temperature of 100 degrees centigrade. The right-hand column indicates the final time, meaning that the time the oven will spend at 100 degrees before continuing the program. In level 2, we are changing the rate to 6 degrees per minute, out to a final temperature of about 222 degrees centigrade. Then the oven will hold the temperature for an additional 5 minutes before ending the run. We have only one injection port in our instrument, and it is injector B. We have set it to 220 degrees Celsius for this demonstration. 280 degrees is the maximum. Our mass spectrometric detector is also in position B. 280 degrees centigrade is the recommendation from the manufacturer for this setting. On the right-hand side, we set the beginning temperature for the oven. It is possible to run the entire experiment at one temperature. This is called an isothermal experiment. However, we are often faced with the need to separate a mixture of compounds over a wide range of boiling points. This situation is often referred to as the general elution problem. The remedy is to program the temperature starting at a low value in order to give the more volatile compounds a chance to separate, and then raise the temperature gradually to move the less volatile components along at a reasonable amount of time. When you click on another cell in the table, you will see the graph below for the oven program adjust to reflect your last entry. Click OK to move on. On the next screen, we set the controls for the split vent. Once again, on our instrument, this is only applicable to the row marked B. Remember that the amount of material that we are injecting could easily overwhelm the loading capacity of the column. That is, the thin layer of stationary phase on the inside wall of the capillary can easily become saturated. In order to avoid this problem, we typically throw away 90% or more of the sample. We do this by opening a valve called the split vent for the first minute or two at the beginning of the experiment. We will manually set the split vent flow rate later in this demonstration. Here the program will open the vent at the start of the experiment and then close it after 1 minute into the run. Click OK to move on. Click OK to accept the default on the next screen. Give your method a file name of up to 8 characters and click OK. From the main screen, choose Main Panel from the Acquire Data menu. On the next screen, select Acquire Data under the menu Acquire Data. Enter a data file name of up to 8 characters. Incorporating your initials and some sort of numerical code that couples the file name to your notebook entry is a good idea. You can also enter a sample name and additional information here. Once you click OK, the computer takes control of the instrument. You will check to see that the various temperatures you set in your program are stable at the various zones that you specified. The red light on the front panel of the oven will remain on until the various temperatures are stable. Now set the flow rate. The manual controls for the carrier flow are on the lower left-hand side of the front of the oven. The flow rate down the column is controlled by the column head pressure. That pressure is set with this black knob. It is set for about 4 pounds per square inch. This will give us a flow of about 1 to 2 milliliters per minute of helium down the GC column. You will not need to change this setting. We will use this meter to measure the flow out the split vent. Turn on the meter with the button on the right. Connect the free end of the rubber tubing to the outlet at the bottom of the left of the oven. The black knob immediately above the outlet controls the split vent flow. It is labeled Total Flow. To increase the flow from the vent, turn the knob counterclockwise. We leave helium flowing through the system at all times. In order to save helium, we generally leave the flow between 10 and 20 milliliters per minute overnight. In this experiment, we will set the purge flow to about 62 milliliters per minute. Therefore, with a flow out the vent of about 62 milliliters per minute and a flow down the column of about 1 milliliter per minute, only about 1.6% actually goes down the column. We sacrifice some signal intensity, but we gain resolution in the separation process. Turn the flow meter off by holding down the button until the meter displays "Have a nice day." During the process of injecting sample, you will need to handle the syringe needle. Since there are natural oils that are volatile on your skin and other possible contaminants on your fingers, wash your hands thoroughly and dry them before proceeding. Prepare the sample for injection inside the fume hood. This is a 10 microliter syringe. We will first rinse out the syringe with a volatile solvent. We will be using ethyl acetate in this demonstration. Draw the liquid into the syringe and expel it onto a paper towel 5 or 6 times. You should be able to see a drop of liquid hit the towel if the syringe is functioning properly. Contamination from one sample to the next can be a problem. Ask your instructor about other cleaning methods if this is a concern in your work. After the syringe is clean, draw approximately a microliter of solvent into the syringe. Remove the needle from the liquid and draw a microliter of air into the syringe. Now place the needle into the bottle with sample and draw approximately half a microliter or less into the syringe. Remove the needle from the sample and draw more air into the syringe. You should be able to see 2 segments of liquid in the barrel. Next to the metal plunger is solvent. A bubble of air separates it from the small segment of sample liquid. This strategy will help you deliver your sample completely to the injection port, since the plug of solvent will rinse out the needle and expel more of your sample. Now we are ready to proceed with the injection. On our instrument, the injection port is accessible from the top of the instrument on the left. Be careful not to touch the green metal cap. Recall that the injector is at 220 degrees centigrade. Although the cap is not nearly that hot, it still can hurt when you touch it. Below the cap is a rubber septum. Use your fingers to grip the needle as it pierces the septum. There is a metal plate with a small hole immediately below the rubber septum. The needle must be perpendicular to the cap to pass through the hole in the bottom plate. By gripping the needle as shown here, you can easily tell if you run into that plate. If that happens, merely pull the needle out and try again. We bend fewer needles using this strategy. The plunger on this syringe is also susceptible to bending. If the plunger bends, it is ruined. Since the manufacturer matches the plunger to individual syringes, finding a replacement plunger is a matter of luck. Think about pushing the plunger straight down as you inject, and you will avoid bending the plunger. Once the needle pierces the septum, push the syringe all the way down so the glass touches the metal cap. Immediately push the plunger down quickly and press the start button on the front end of the oven. Once the needle pierces the septum, you should finish the process within 2 seconds. Otherwise, the material from the inside of the needle will get a head start over the rest of the sample, and extra peaks will appear in your chromatogram. The computer will ask you whether you want to override the solvent delay and begin taking data immediately. Say no. As you get more experience with the instrument, you will learn techniques in which overriding the solvent delay is appropriate. However, this is a protection measure for the detector, so for now, say no. Once the mass spectrometer turns on, you will see a signal that represents the total ion count from each individual scan on the vertical axis and time on the horizontal axis. You can increase or decrease the sensitivity of the y-axis by entering a new number in the box on the upper right side of the screen. This affects the display only. Nothing you do to the display will change the way the data is stored. Narrow peaks are characteristic of a good GC experiment. Peaks should be only a few seconds wide at the bottom in the beginning of your chromatogram. You may stop the experiment early by using the button in the lower left. You can also extend the run in increments of 5 minutes using the button in the center of the graph. At the end of the experiment, your data is saved automatically. Return to the main screen and select Main Panel under the Data Analysis menu, and under File choose Load. Most likely your data file name will appear as the selected file on the next screen. If not, scroll down the alphabetical list to find it. The computer will display the chromatogram in the top half of the screen. It automatically adjusts the y-axis so the tallest peak reaches the top of the graph. You can zoom in on just a portion of the chromatogram by holding down the left-hand mouse button and dragging the cursor from below the x-axis to the top of the screen, creating a box around the portion you would like to enlarge. Enlarging a region of interest makes it easier to position the cursor precisely on a peak. If we double-click the right-hand mouse button, the computer will display the mass spectrum from whatever was in the detector at that moment in time, corresponding to the position of the cursor on the chromatogram. In order to display precise intensity data at given masses, select Tabulate from the Spectrum pull-down menu. Only a portion of this table is visible on the screen at any given time. Use the tab on the right-hand side to scroll to other parts of the table. Select Done before proceeding. We might be able to identify this compound based on the mass spectrum by matching it with a spectrum from a library from the National Institute of Standards and Technology. Under the Spectrum menu, select NIST Output. Select Create a File with Spectrum in X. Click OK. Then select Toggle to NIST Search Program. Click OK. Your spectrum will now appear in the upper right-hand portion of the screen. Below that will appear a spectrum that corresponds to the closest match from the library. Structures for other candidates that have similar spectra appear in the lower left-hand window. Scroll through the candidates with the tab on the right side of that window. By clicking on the diagram, you can open and display the corresponding spectrum from that structure from the library. Another helpful feature is to be able to search the chromatogram for compounds that exhibit a specific fragment ion. Under the chromatogram menu, select Extract Ion Chromatograms. In this table, you can specify the mass of specific ion fragments of interest. In this example, we will search the chromatogram for peaks that contain fragments at atomic mass unit 91. This fragment is characteristic of toluene and alkylbenzene compounds. The computer will redraw the chromatogram to show you only those peaks that contain an ion mass at 91. This can greatly simplify the chromatogram and speed up your search for specific compounds. If you wish to print your results on the screen, select the printer setup from the File menu and choose the Portrait or Landscape mode. Now choose Print from the File menu. You have the option of printing only one window, either the chromatogram or the spectrum only, or a combination of the two. When you are finished with the GC, set the flow at the split vent back to the value between 10 and 20 milliliters per minute. Be sure to turn off the flow meter. Finally, log your time on the instrument in the logbook in the drawer below the computer.